Radiation. All temperature must be in Kelvin. Wavelength module. Sun radiation 0.1 micrometer to 100 micrometer. Thermal radiation. Sun radiation. Electromagnetic spectrum. Directional module. Any body will emit thermal radiation in all possible hemispherical directions integrated overall the wavelength considered on electromagnetic spectrum. Total hemispherical emissive power E. It is defined as radiation energy emitted from surface of body per unit time per unit area in all hemispherical directions integrated overall the wavelengths. E is equal to joule per second per meter square is equal to watt per meter square. Total emissivity E. Total emissivity epsilon. It is defined as ratio between total hemispherical emissive power of a non-black body and total hemispherical emissive power of black body, both being at same temperature. Epsilon is equal to E by EB for any body, epsilon less than or equal to 1. For black body, epsilon be equal to 1. Black body is a body which absorbs all thermal radiation incident or falling upon the body. Here everything is absorbed and everything is reflected back. Since, a narrow or tiny cavity in a hollow container can be treated as black body since all thermal radiation incident upon the cavity will be absorbed after multiple internal reflection. Example, a small hole or cavity in furnace wall. In radiation analysis, sun is treated as black body, perfect absorber, ideal emitter, diffusive. Monochromatic spectral hemispherical emissive power E lambda joule per second per meter square micrometer, watt per meter square micrometer. E lambda at any particular wavelength lambda is defined as a quantity which were multiplied by d lambda shall give an radial and radiation energy emitted from the surface of the body per unit time per unit area in wavelength region lambda to lambda plus d lambda for any given body at a given temperature. E lambda is equal to f of lambda. E is equal to integral 0 to infinity E lambda d lambda watt per meter square lambda to d lambda plus d lambda. This E lambda and lambda total hemispherical emissive power area is total hemispherical emissive power. Monochromatic or spectral emissivity epsilon lambda. It is defined as ratio between monochromatic hemispherical emissive power of non-black body and monochromatic emissive power of black body, both being at same temperature and wavelength. Epsilon lambda is equal to E lambda by EV lambda. E lambda is equal to E lambda epsilon lambda into EB lambda. Total emissivity E epsilon is equal to E by EB is equal to integral 0 to infinity E lambda d lambda by integral 0 to infinity EB lambda d lambda. E lambda is written as epsilon lambda EB lambda dx. Here epsilon denominator remains same. If a epsilon lambda is not function of f of x or rather constant, then epsilon is equal to epsilon x. Both these two will cancel and epsilon is equal to epsilon x, epsilon lambda. Such body whose monochromatic emissivity is independent of wavelength or remaining constant is known as gray body. Physical significance of gray body. For a gray body, epsilon lambda 1 is equal to epsilon lambda 2 is equal to epsilon lambda 2. E lambda 1 by EB lambda 1 is equal to E lambda 2 by EB lambda 2. Gray body, black body, okay, this ratio remains same. The ratio between area under bottom curve on x-axis and area under top curve on x-axis will be equal to total emissivity of gray body, which happens to be equal to its monochromatic emissivity. For non-gray body, epsilon lambda is equal to f of lambda. The non-gray body do not touch black body curve. Non-gray body, it will be like this. It will not. Absorptivity alpha. fraction of radiation energy incident upon surface which is absorbed by it. Here 100 units of the thermal radiation incident, 25 units transmitted, 25 units reflected. That means 50 is absorbed. Alpha is equal to 0.5 in this case. Reflectivity, fraction of radiation energy incident upon surface which is reflected by it. Transmissivity, fraction of radiation energy incident upon the surface which is transmitted through it. This is transmitted through it. Okay, for any surface alpha plus rho plus tau is equal to 1. For opaque surface which does not transmit any energy, tau is equal to 0. For opaque surface alpha plus rho is equal to 1. Metallic surfaces aluminum, copper have high reflectivity. This is the reason why metallic sheets are generally used in furnace to reduce radiation heat exchange. Gases like O2, N2, etc. have high transmissivity, transparent to thermal radiation. The above radiation properties mentioned change with wavelength of incident radiation, surface roughness of the body, and also with its temperature. Example, window glass of car is very much transparent to short wavelength solar radiation, but same window glass almost becomes opaque to long wavelength radiation given inside of the car, thus trapping energy inside the car, hence increasing its temperature. That is why if you keep car in sun, it will be too heated inside. As the surface roughness of body decreases by polishing it, the reflectivity of surface will increase. This is the reason why highly polished metallic sheets have having good reflectivity and are generally used in furnaces to reduce radiation heat exchange. CO2 also same reason, like CO2 greenhouse gas, short wavelength it will let it enter, but long wavelength it will not let it leave. Laws of thermal radiation, Kirchhoff's law of thermal radiation. The law states that whenever the body is in thermal equilibrium with its surroundings, its emissivity is equal to absorptivity. Epsilon is equal to alpha. Epsilon is equal to alpha. A good observer is always a good emitter. Example, black body. Alpha B is equal to 1, epsilon B equal to 1. Planck's law of thermal radiation, EB lambda is equal to F of lambda comma T. The law states that monochromatic emissive power of a black body is dependent on both absolute temperature of black body and also on wavelength of radiation energy emitted lambda. EB lambda is equal to F of lambda at comma T. EB lambda is equal to 2 pi C1 by lambda power 5 e power C2 by lambda T minus 1 watt per meter square micrometer. C1 and C2 are constants. Wien's displacement law, the above functional relationships among the three variables can be graphically represented as lambda m, wavelength at which EB lambda is maximum at a given absolute temperature of black body. Lambda m3 by lambda m1 is equal to 1 by 4 hyperbolic. If you join the peaks, lambda it will move in this direction. Temperature, as temperature increases, it will move in this direction at a given absolute temperature of a black body. As wavelength lambda increases, EB lambda also increases, reaches a maximum and then decreases. Also, as absolute temperature of black body increases, each time getting doubled, EB lambda values enormously increase. But now most of thermal radiation at higher temperature will be shifted to shorter or smaller wavelengths. As T increases, lambda m decreases. Lambda m inversely proportional to T in Kelvin. Lambda m into T is equal to constant is equal to 2898 micrometer Kelvin. Optical pyrometer uses this principle. This equation is called Wien's displacement law. For solar radiation, lambda m into T is equal to 2898 micrometer Kelvin. Lambda m is equal to 898 by 5800 Kelvin. Lambda m is equal to half micrometer. Stephen Boltzmann law. The law states that the total hemispherical emissive power of a black body is directly proportional to fourth power of absolute temperature of body. EB directly proportional to T power 4. EB is equal to sigma T power 4 watt per meter square. Sigma is equal to Stephen Boltzmann constant is equal to 5.67 into 10 power minus 8 watt per meter square Kelvin power 4. The ratio between topmost curve on x-axis and area under bottommost curve on x-axis will be 2 4 power 4, that is okay 256. Their case as temperature is there. EB is equal to integral 0 to infinity EB lambda d lambda is integral 0 to infinity. This integration is equal to sigma t power 4 watt per meter square. For non-black body whose emissivity is epsilon, total hemispherical emissive power of non-black body is equal to epsilon EB watt per meter square is equal to epsilon sigma T power 4 watt per meter square. If A is the surface area of non-black body, then total radiation energy emitted from entire non-black body is equal to E A watt is equal to epsilon sigma T power 4 A watt. T1 by T2 is directly proportional to whole power 4. We can use that and get it. Wien's displacement law, lambda m into T is equal to constant. Lambert's cosine law, directional module. I is equal to In cos theta. In is equal to normal intensity of radiation. I is equal to intensity of radiation along any direction making an angle theta with respect to normal. Steradian is equal to unit of solid angle. Intensity of radiation I. Intensity of radiation along any given direction is defined as radiation energy emitted from surface of the body per unit time per unit area normal to the direction. I joule per second meter square steradian is equal to watt per meter square steradian, and per unit solid length angle about line about that direction. I is equal to dE by d omega watt per meter square steradian. Total emissive power is equal to E is equal to integral I dW watt per meter square. Intensity of radiation. Diffusive surface has the same intensity of radiation along all directions. That is, for a diffusive body that is independent, I is independent of direction. Example, black body is a diffusive surface. For black body, EB is equal to I pi watt per meter square. Shape factor or view factor or configuration factor, F12 is equal to, here in this case, 50 units, 600 units leaving, 60 units reaching. Okay, 100 units leaving, 50 units reaching. Okay, is equal to 60 by 100 is equal to 0.6. Fraction of radiation energy leaving surface 1 and reaches surface 2. F21 0.5, 50 by 100. Fraction of radiation leaving surface 2 and reaches surface 1. FMM, fraction of radiation energy leaving surface M that reaches surface N. 0 less than or equal to FMN less than or equal to 1. Note the shape factor between two surfaces is independent. Their temperatures, their emissivities, wavelengths of emissions, but depends only on their sizes and shapes and how closely the two surfaces are kept with respect to each other. Flat surface F1 is equal to 0. Concave surface F11 greater than 1, convex surface F11 equal to 0, F21 greater than F12. When one body of surface is completely surrounded by another body or surface, the shape factor of inner body with respect to outer body is equal to 1. F21 plus F22 is equal to 1. F12 is equal to 1. Semi-spherical dome, circular form. Two concentric spherical shells, F12 is equal to 1, F21 is less than 1, F22 less than 1, F21 plus F22 equal to 1. Two infinitely long concentric cylinders, same case, F12 is equal to 1, F21 less than 1, F22 less than 1, F21 plus F22 equal to 1. If cylinders are of finite length, F12 less than 1, F21 less than 1, F22 less than 1, F21 plus F22 less than 1. Body kept in a room on an enclosure. F12 is equal to 1, F21 less than 1, F22 less than 1, F21 plus F22 equal to 1. Reciprocity relation between shape factors. A1 F12 is equal to A2 F21. Here A means area. F22 is equal to question mark for circular body. F12 is equal to 0. F21 is equal to A1 by A2. A1 by A2 is equal to pi r square by 2 pi r square is equal to half. But F21 plus F22 is equal to 1. F22 is equal to half. Okay. Solid cylinder inside sphere. All dimensions are given. F21 is equal to 1. A1 F21 is equal, A1 F12 is equal to A2 F21. From that F11 we can find it by F11 plus F12 equal to 1. Okay. Shape factor in case of conical cavity having a semi-vortex angle A and height h is given by, okay, this is 1 and this is 2 alpha. Okay, f12 is equal to question mark, f21 is equal to 1, a1 f12 is equal to a2 f21, f12 is equal to a2 by a1 is equal to pi r square by pi r l, pi r l is equal to r by h is equal to sine alpha. This A1 area is pi r h. Okay, is equal to sine alpha. Summation rule among shape factors. If there are n number of surfaces involved in the radiation heat exchange problem, then f11 plus f12 plus f13 so on f1n is equal to 1. Similarly for 2 and n, yeah, so on n. If any particular surface, either flat surface or convex surface, then its self shape factor becomes 0. Even now, reciprocity relation is valid between any two surfaces. A2 F23 is equal to A3 F32, A1 F14 is equal to A4 F41. Okay, one question using same principle we can get it. From symmetry, F21 is equal to F23. Okay. This is also same F11 0, F12 plus F13 is equal to 1. Similarity is equal to half. F21, F12, again using the same problem, A1 and A2, we can get it. Using two those principles only, you can get it area and summation rule. A very small body kept in a very large enclosure. F12 is equal to 1. F21 is equal to A1 by A2 into F12. A1 less than A2. F21 is equal to 0. Examples: filament in a bulb, thermocouple in a duct. Radiation heat exchange between two infinitely large parallel plates. Case 1, assume steady state heat transfer conduction surfaces are diffuse and gray. T1 greater than T2. Q by A is equal to sigma into T1 power 4 minus T2 power 4 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1 watt per meter square. Okay, two bodies just using the formula. Okay. Okay, case 2. Radiation heat exchange between two concentric infinitely long cylindrical surfaces. Okay. F12 is equal to 1, T1 greater than T2, F21 less than 1. The outer surface of inner cylinder at T1 Kelvin is exchanging heat by radiation with inner surface of outer cylinder at T2 Kelvin. Assume steady state heat transfer conditions T not equal to F of time. Surfaces are diffuse and gray. Epsilon lambda is equal to C. I not equal to F of direction. Then net radiation heat exchange between 1 and 2 is Q12 is equal to sigma into T1 power 4 minus T2 power 4 into A1 by 1 by epsilon 1 plus A1 by A2 1 by epsilon 2 minus 1. A1 by A2 is equal to 2 pi R1L by 2 pi R2L is equal to R1 by R2. R1 by R2. Here 1 is inside, 2 is outside. Net radiation heat. The above case 2 formula is applicable for all radiation heat exchange cases between two surfaces whenever one shape factor between them is equal to 1 and other shape factor is less than 1. The same formula is also valid when T2 greater than T1, but precaution is that always the number inner surface as 1 and outer surface as 2. Examples, hemispherical f12 is equal to 1, f21 less than 1, a1 by 2 is equal to two concentric spherical surfaces f12 is equal to 1, f21 less than 1, a1 by 8 is equal to r1 square by r2 square. A very small body in a very large enclosure, f12 is equal to 1, f21 less than 1, a1 by a2 tends to 0. q12 is equal to sigma into t1 power 4 minus t2 power 4 into a1 into epsilon 1. That whole term with this thing goes to 0 as a1 by a2 is almost equal to 0. Filament sigma t1 power 4 minus t2 power 4 into a1 epsilon 1. Here epsilon 1 and 1 should be this inside one. To get the error in temperature measurement of gases by using thermocouple, Tg is equal to true gas temperature, Tc is equal to temperature recorded by thermocouple, Tw is equal to duct wall temperature. Thermocouple receives heat by convection from hot flowing gases, which in turn exchanges heat by thermal radiation with duct walls. Duct Tw hot gases at Tg, Tc thermocouple bead radiation exchange. For a steady state condition, thermocouple bead writing energy balance equation. The rate of convection heat transfer between hot gases and thermocouple is equal to net radiation heat exchange between thermocouple and duct walls. Newton's law of cooling, HA Tg minus Tc is equal to sigma into Tc power 4 minus Tw power 4 into epsilon A watt. All in Kelvin. Dg minus Tc is error. Tc power 4 minus Tw power 4. Experiment hot flue gases. Okay. Convective heat transfer H. Here a formula is given. So RE rho d by mu H finally H is there. HA into Tg minus Tc is equal to sigma into Tc power 4 minus Tw power 4 epsilon Tc into A. Error in measurement is Tg minus Tc. Okay. Error in measurement can be reduced by increasing convective heat transfer coefficient H, that is by providing more velocity to gases, decreasing emissivity of thermocouple bead by polishing it, by increasing the duct wall temperature Tw, that is insulating duct outside. Okay, F1 to Q1 is equal to sigma into T1 power 4 minus T2 power 4 into A1 by 1 by epsilon 1 plus A1 by A2 into 1 by epsilon 2 minus 1. And 1 by epsilon 2 minus 1, this whole thing is 0, sigma 1 A1 epsilon 1 T1 power 4 minus T2 power 4. Radiation networks. From this radiation network technique, we can calculate net radiation heat exchange between any two finite or infinite diffusive gray or black surfaces, irradiation G and radiosity J. The thermal radiation incident upon surface per unit time and per unit area is known as irradiation. That is G. The total radiation energy, radiation leaving a surface per unit time per unit area is known as radiosity J. J is equal to energy emitted plus energy reflected by incident energy. J is equal to E plus rho G watt per meter square. J is equal to epsilon EB plus rho G watt per meter square. J is equal to epsilon EB plus 1 minus epsilon into G watt per meter square. Alpha plus rho plus tau is equal to 1 for any surface. Alpha plus rho is equal to 1 for opaque surface. Rho is equal to 1 minus alpha. Rho is equal to 1 minus epsilon. Alpha is equal to epsilon. Kirchhoff's law. The net heat exchange between the surface at area A and all its surroundings will be Q net is equal to J minus G into A. What G is equal to J minus epsilon EB by 1 minus epsilon. Q naught is equal to epsilon EB plus 1 minus epsilon into G minus G into A. Eliminating G, we can get Q naught is equal to EB minus J by 1 minus epsilon by epsilon A watt. EB J Q net surface surroundings 1 minus epsilon by epsilon A, which is surface resistance. The equivalent thermal radiation circuit. The surface resistance shall exist at every surface which is exchanging heat thermal radiation with all its surroundings. Consider two finite surfaces of areas A1 and A2 having the radiosities J1 and J2 exchange heat by thermal radiation as shown in figure. Out of total radiation leaving surface 1 and the surface energy that is reaching surface 2 is J1 A1 F12. Similarly, out of total radiation energy leaving surface 2, the energy that reaches surface 1 is J2A2 F21. J2A2 F21. The net radiation heat exchange between 1 and 2 Q12 net is equal to J1A1 F12 minus J2A2 F21 watt. A1 F12 is equal to A2 F21. So Q net is equal to J1 minus J2 into A1 F12. Q net is equal to J1 minus J2 by 1 by A1 F12. The corresponding thermal radiation circuit is this. J1 or J2 Q1 to net by 1 by A1 F12 space resistance. The space resistance shall exist in space or gap or vacuum prevailing between two surfaces which are exchanging heat by radiation. Hence, a complete radiation network for radiation heat exchange between two finite diffuse gray surfaces is given by 1 by F12. If in case if both surfaces are black, then epsilon 1 is equal to epsilon 2 is equal to 1, then we have space resistance only. AB 1 by A1 F12 as 1 minus epsilon by 1 minus epsilon 1 by A1 epsilon 1 is 0. Okay, if they are normal, Q12 is equal to sigma into T1 power 4 minus T2 power 4 by 1 minus epsilon 1 by epsilon 1 A plus A1 by A1 F12 plus 1 minus epsilon 2 by epsilon 2 A2. For black body, only 1 by A1 F12 will be there. Application of radiation network method. Case 1 to infinitely large parallel plate network EB1, EB2, 1 minus epsilon 1 by A1 epsilon 1, 1 by A1 F12, 1 minus epsilon 2 by A2 epsilon 2. Since plates are being very large, A1 is equal to A2 is equal to 1, therefore, since flux calculated. Q by A is equal to sigma into T1 power 4 minus T2 power 4 by keep all A's 1 F12 is equal to 1. So Q by A is equal to sigma into T1 power 4 minus T2 power 4 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1 watt per meter square, which is similar to before. Infinitely long concentric cylindrical surfaces F12 is equal to 1. So A1 minus epsilon 1 by A1 epsilon 1, 1 minus epsilon 2 by A2 F2. Okay, Q12 net is the sigma into T1 power 4 minus T2 power 4 by 1 by epsilon 1 A1 minus 1 by A1 plus 1 by A1 plus 1 by epsilon 2 A2 minus 1 by A2. This 2 will cancel, and multiplying numerator and denominator with A1, Q12 net is equal to sigma into T1 power 4 minus T2 power 4 into A1 by 1 by epsilon 1 plus A1 by A2 into 1 by epsilon 2 minus 1 watt. Radiation shields network. This shield of epsilon 3 will be there, epsilon 1, epsilon 2. This has this surface will have one resistance, this surface will have one resistance, and the between these two one gap, between these two one gap. So F13 is equal to F32 is equal to 1. Q12 net is drawing Q12 net is equal to sigma into T1 A1, put A1 is equal to A3 is equal to 1, sigma into T1 power 4 minus T2 power 4 by 1 by epsilon 1 plus 2 by epsilon 3 plus 2 by epsilon 3 plus 1 by epsilon 2 minus 2. Hence, to reduce radiation heat exchange by a very good percentage by keeping shield. The shield placing between plates must have low emissivity or very high reflectivity, for which highly polished aluminum or copper shields having very good reflectivity are used. Each shield kept between plates shall bring in 3 additional resistance extra into network, out of which 2 are surface resistance and the remaining one is space resistance. Hence, there are n number of shields being kept between plates, then there would be total 2n plus 2 number of surface resistance and n plus 1 total number of space resistance in an entire radiation network drawn with n number of shields. Special case, in case if all surfaces, planes as well as shields are having same emissivity, epsilon 1 is equal to epsilon 2 is equal to epsilon 3 is equal to epsilon, then q by a no shield is equal to sigma into T1 power 4 minus T2 power 4 by 2 by epsilon minus 1 watt per meter square. Q by A with one shield is equal to sigma into T1 power 4 minus T2 power 4 by 4 by epsilon minus 2. Half, if you remove half outside, Q by A is equal to 1 by 2 into Q net without shield. Then if there are n number of shields are being kept, Q by A net and shields is equal to 1 by n plus 1 Q by A without any shield, provided all epsilon planes we also are same, epsilon is same for all. One shield 50% reduction, 2 66.6, 3 75%, 4 80% reduction. Okay, two very large plates. Okay, one polished radiation shield is there, a direct formula. QA with shield, QA with shield, percentage reduction. This is general. Here question is, if you plate 1 diffuse and gray, net radiation heat exchange between 1 and 2. Between 1 and 2. Radiation of 2 is equal to EB1. EB1 radiation of 1 is equal to G1 is equal to total thermal radiation incident upon 1, which is 1 minus epsilon 2 into EB1 plus epsilon 2 EB2. Epsilon 2 EB2 is the one that is reaching 1, and this EB1 that has been incident on this is reflected back, that reflect into reflection rho is 1 minus epsilon 2. From that we get G1. Okay, radiosity J, radiation of 1 and radiation of 2. Okay, radiosity J is equal to E plus rho G. J is equal to E plus rho G. Radiosity is leaving the surface, E plus rho G. Emissivity J is equal to E plus rho J. Rho is equal to 1 minus epsilon. From that we can find epsilon. Insert 3 cylinders. Then from that we can get all these resistance normal only, but lengthy. 1, 2, 3, 4, infinite line, infinite fence. Q net from surface. Okay. Sigma 2 into the net radiation loss is equal to this all resistance Q13. EV1, J1, J3, EV2, EV1, then total net radiation loss is equal to 2 into Q1 to Q net from 1, 2 into sigma T144 minus T244 by 1 by A1 F12, 2 into, okay. Okay, and this epsilon minus epsilon 1 by epsilon E1 minus epsilon, this 0, 0, black body. Okay, just drawing circuits.